Look up into the night sky and you are gazing across a cosmic ocean populated by hundreds of billions of stars, each potentially anchoring alien worlds that challenge everything we understand about planetary science. For generations, humanity could only evaluate the familiar neighborhood of our own solar system, where rocky inner planets and outer gas giants orbit along well-behaved, stable paths. Modern observational astrophysics has shattered those initial assumptions, cataloguing thousands of alien worlds scattered across our galaxy. Many of these newly discovered bodies push physical mechanisms to their theoretical thresholds, testing our contemporary models of thermodynamics, orbital resonance, and atmospheric behavior. Some exist so close to their stellar hosts that intense radiation may be stripping their upper atmospheres away into streaming tails of gas, while others wander through the frigid interstellar void without a parent star in sight. Today, we are going to explore the most extreme exoplanets we have ever found. As we begin our journey into these extraordinary worlds, feel free to give this video a like and subscribe if you enjoy exploring the frontiers of space science. We would also love to know where you are watching from and what time of day or night it is right now, so please leave a quick comment below. Let us begin our journey across the cosmos to witness how radical planetary environments can truly become. When astrophysicists discuss thermal extremes, no conversation can begin without examining the remarkable system of Kelt 9b. Discovered through the Kilo-degree Extremely Little Telescope survey, this gas giant resides roughly 670 light-years away from Earth, in the constellation Cygnus. In the lexicon of modern astronomy, Kelt 9b is classified as an ultra-hot Jupiter, a designation reserved for gas giants that orbit astonishingly close to their host stars. Yet even among this exotic class of celestial bodies, Kelt 9b occupies a regime of its own. It presents one of the most hostile thermal laboratories currently known to science, challenging our standard models of planetary atmospheres and stellar radiation dynamics. To understand the extraordinary conditions on this planet, one must first look at the host star, Kelt 9. Unlike our Sun, which is a relatively calm yellow dwarf star with a surface temperature hovering around 5,500 degrees Celsius, Kelt 9 is a massive, rapidly rotating A-type star, nearing the spectral classification of a B-type star. Its surface temperature approaches 10,000 degrees Celsius, emitting copious amounts of high-energy ultraviolet radiation. Kelt 9b orbits this roaring nuclear furnace at a proximity that strains the imagination. The planet completes an entire journey around its parent star in roughly 36 hours. Because it is so close, gravitational interactions have almost certainly locked the planet into synchronous rotation, an astrophysical state where the same hemisphere perpetually faces the scorching stellar surface, while the other remains turned toward the darkness of space. The consequence of this extreme proximity to an exceptionally hot star is an atmospheric temperature on the planetary day side that scientists estimate to exceed 4,300 degrees Celsius. To put that figure into perspective, this makes the permanent day side of Kelt 9b hotter than the surfaces of many low-mass stars, particularly red dwarf stars and brown dwarfs. At such temperatures, the physical behavior of matter departs drastically from anything observed in the solar system. Under original planetary conditions, atmospheric gases consist of molecules such as water vapor, methane, or carbon dioxide. However, current theoretical models and spectroscopic data suggest that the energetic environment of Kelt 9b prevents these chemical structures from remaining intact on the day side. The intense ultraviolet flux and relentless thermal energy appear to drive a process known as thermal dissociation. In this state, the kinetic energy of the atmospheric constituents becomes higher than the chemical binding energies holding molecules together. Water vapor, molecular hydrogen, and other compound species are violently torn apart into their constituent neutral and ionized atoms. High-resolution transit spectroscopy has provided evidence for vapors of atomic iron, titanium, and other heavy metals floating freely in the upper atmosphere. In most planetary contexts, iron and titanium exist only in liquid or solid mineral forms, locked deep within cores or rocky mantles. On Kelt 9b, the environment is so relentlessly energetic that iron is suspected to behave as a volatile atmospheric gas, occupying the same gaseous role that water vapor occupies in the atmosphere of Earth. The transfer of thermal energy on this world is a subject of active research and scientific debate. Under the principle of tidal locking, one might initially assume that the night side would cool down significantly, acting as a massive heat sink. However, atmospheric dynamicists hypothesize that powerful global circulation patterns, driven by the massive temperature differential between the two hemispheres, attempt to transport energy from the permanent noon to the permanent midnight. These atmospheric currents are thought to manifest as supersonic winds flowing along the equator and across the planetary limbs. As these intense winds carry dissociated atomic gases toward the cooler night side, numerical simulations suggest an intriguing mechanism known as molecular recombination. When the gas travels into regions of lower temperature, the individual hydrogen atoms and metal constituents can once again bond together, releasing latent heat in the process. This chemical recombination acts as an efficient conduit for transferring energy across the planetary globe. Once the winds carry the reformed molecules back into the intense radiation field of the dayside, the dissociation cycle begins anew. Scientists emphasize that these atmospheric flow models remain informed inferences, as our current instruments can only measure average temperature variations across broad spatial regions rather than resolve local wind currents directly. Another major scientific question surrounding Kelt 9b is its long-term survival under such extreme stellar bombardment. The intense ultraviolet radiation from the host star does not merely heat the atmosphere, it also inflates it to immense physical proportions. The outer envelope of the planet puffs up, significantly lowering the local gravitational hold on the outermost gas layers. Consequently, hydrodynamic escape models propose that the planet is losing its atmosphere at an extraordinary rate, potentially shedding tens of millions to billions of grams of gas every single second. This outflow may form a giant comet-like tail of escaped vapor trailing behind the planet along its orbital path. Whether this atmospheric escape will eventually strip Kelt 9b down to a bare, solid remnant core, or whether the host star will evolve off the main sequence and engulf the planet before that can happen, remains an open theoretical question. Stellar evolution models suggest that massive A-type stars possess relatively short lifespans, burning through their hydrogen fuel reserves in a few 100 million years. Kelt 9 is young in astronomical terms, but its rapid evolution means the clock is ticking for its planetary companion. The planet exists in a delicate and fleeting astronomical epoch, where the rate of atmospheric mass loss races against the inevitable expansion of its dying parent star. Studying Kelt 9b has forced planetary scientists to bridge the gap between classical meteorology and stellar astrophysics. In many respects, the atmospheric physics of this planet resembles the outer layers of a low-mass star more closely than it resembles any conventional planet. The presence of free metal atoms, partial ionization, and chemical dissociation pathways introduces complex opacity sources that alter how the planet absorbs and radiates energy back into space. Planetary researchers continue to monitor this world using space-based and ground-based observatories to refine temperature maps and test predictions regarding its exotic atmospheric chemistry. In summary, Kelt 9b stands as an extraordinary demonstration of physical extremes. It illustrates how astronomical proximity and stellar classification can reshape the very nature of matter on a planetary scale. While many questions remain regarding the precise efficiency of its day-to-night heat redistribution and the exact magnitude of its atmospheric loss, the current body of evidence paints a portrait of a world pushed to the absolute thermodynamic brink. It serves as a vital benchmark for testing the limits of planetary existence, demonstrating that beneath the light of massive stars, worlds can exist whose skies burn with the fury of gaseous metal and unbound atoms. Situated approximately 64 light-years from Earth in the northern constellation of Vulpecula, the exoplanet HD 189733b represents one of the most comprehensively analysed alien worlds in contemporary astrophysics. Discovered in the mid-2000s, this celestial body is classified as a classic hot Jupiter, possessing a mass slightly greater than that of Jupiter while orbiting its host star at an extraordinarily tight distance. The planet completes a full orbital revolution in roughly 2.2 Earth days, tracing a path that brings it millions of kilometers closer to its parent star than Mercury is to our Sun. At first glance through the speculative lens of artistic rendering, one might envision an inviting and serene oasis, because multiple observational datasets have revealed that the planet reflects light with a rich, vibrant azure tone, reminiscent of Earth seen from orbit. However, rigorous astrophysical data and theoretical modeling paint a reality that is anything but calm, revealing a fiercely turbulent world dominated by extreme atmospheric dynamics and exotic chemical weather. To understand why HD 189733b exhibits its striking blue coloration, planetary scientists have turned to the physical principles of optical spectroscopy and light scattering. On Earth, our sky appears blue primarily because of Rayleigh scattering, a process where tiny molecules of nitrogen and oxygen scatter shorter blue wavelengths of sunlight far more efficiently than longer red wavelengths. For HD 189733b, early photometric and polarimetric measurements obtained through space-based observatories confirmed a distinct drop in reflectance toward the redder portions of the spectrum, paired with strong scattering at blue wavelengths. Yet the underlying mechanism differs fundamentally from terrestrial physics. The atmosphere of this gas giant is far too hot for simple molecular nitrogen to dominate the scattering profile in the same manner. Instead, scientists hypothesize that the blue appearance arises from a combination of strong optical absorption by vaporized alkali elements, such as atomic sodium and potassium, coupled with the intense scattering of light off high-altitude mineral condensates suspended within the upper atmospheric layers. The thermal structure of HD 189733b provides the foundation for these extraordinary conditions. Because the planet orbits so close to its parent orange dwarf star, it is exposed to relentless stellar irradiation, sustaining daytime atmospheric temperatures that models estimate to range between 900 and 1200 degrees Celsius. Gravitational tidal forces acting over millions of years are widely believed to have synchronized the planet's spin with its orbital period. Under this tidal locking scenario, the planet possesses a permanent day side, bathed in perpetual stellar light, and a permanent night side facing the cold vacuum of space. This continuous asymmetric energy injection generates an immense thermal contrast between the two hemispheres, driving some of the most violent meteorological phenomena ever investigated. The transfer of thermal energy from the blistering day side to the cooler night side does not occur gently. Atmospheric dynamicists utilize complex three-dimensional general circulation models to simulate how such massive temperature gradients resolve themselves across a rotating gaseous sphere. These theoretical models predict that the planetary atmosphere establishes an intense equatorial superrotation, characterized by a massive continent-sized jet stream that circulates eastward around the planet. Observational support for these high-speed winds emerged when astronomers applied high-resolution infrared spectroscopy to measure the Doppler shifts of carbon monoxide absorption lines as the planet transited its host star. By tracking the slight shifts in the wavelengths of light absorbed by the gas moving toward and away from the observer, researchers inferred atmospheric velocities reaching approximately 7,000 to 8,700 kilometers per hour. To place that velocity in context, these winds travel at more than 2 kilometers per second, easily exceeding the local speed of sound within the planet's heated hydrogen-helium envelope. Such supersonic winds would whip across the terminator, the boundary line separating day from night, with enough kinetic force to distort atmospheric layers and generate immense shock fronts. Under these conditions, the meteorology of HD 189733b bears no resemblance to the storm systems found in the solar system. The wind currents are so rapid that they physically displace the hottest point of the atmosphere away from the substellar point, shifting the thermal peak eastward by several tens of degrees of longitude, a phenomenon that has been independently supported by orbital phase curve observations. Beyond the ferocious winds, the composition of the clouds on HD 189733b has captured significant scientific attention, giving rise to the famous hypothesis of glass rain. In the high-temperature chemistry characteristic of hot Jupiter atmospheres, common silicate minerals that form rocks and sand on Earth are not trapped in a solid crust. Instead, at temperatures exceeding 1000 degrees Celsius, compounds such as silicon dioxide, magnesium silicate, and enstatite can exist in vapor phase within the deeper, hotter layers of the atmosphere. As vertical convective currents and large-scale circulation lift this mineral vapor into the cooler upper atmospheric layers and across into the cooler night-side hemisphere, the local thermal conditions drop below the condensation threshold for silicates. When this phase transition occurs, the silicate vapor begins to nucleate, condensing into microscopic droplets and solid aerosol particulates. Theoretical microphysical models suggest that these newly formed grains of silica and magnesium silicates form extensive high-altitude haze layers that blanket the planet. If the condensation process progresses to form larger droplets under local gravity, these mineral particles would precipitate downward through the atmospheric column. However, because the horizontal wind speeds are calculated to be thousands of kilometers per hour, any resulting precipitation would not fall vertically toward the planet's interior. Instead, the silicate particles would be swept sideways in a relentless, globe-spanning torrent of airborne mineral shards. Scientists maintain an important element of caution when describing this phenomenon. It is vital to emphasize that astronomical instruments cannot directly image individual droplets of silicate rain falling through the sky of HD 189733b. Rather, the glass rain concept is an evidence-based deduction derived from matching optical transmission spectra, which exhibit a steep Rayleigh scattering slope without sharp molecular absorption features, with thermodynamic equilibrium models of condensate clouds. Spectroscopic data consistently reveal a muted spectral signature for common volatile molecules like water vapor. This muting is widely interpreted not as a true absence of water, but as the consequence of an optically thick cloud deck, or haze, composed of silicate particulates that obscures the deeper molecular layers from view. The nature of these atmospheric hazes remains an active area of discussion among planetary scientists. While silicate condensation remains the leading theoretical explanation for the observed scattering properties, alternative and complementary models have been proposed. Some researchers investigate whether photochemical hazes, generated when high-energy stellar ultraviolet radiation breaks apart methane and other carbon-bearing molecules, could contribute to the aerosol layer. Others suggest that compounds of iron or sulfur, such as iron sulfide or magnesium sulfide, might also condense at specific altitudes, creating a chemically diverse and layered cloud structure that varies across longitude and latitude. The ongoing study of HD 189733b has fundamentally transformed how astrophysicists conceptualize planetary atmospheres. It has demonstrated that exoplanetary meteorology must integrate high-energy fluid dynamics, non-equilibrium chemical kinetics, and mineral cloud microphysics to construct realistic models. What began as a simple measurement of light dimming during an exoplanet transit has evolved into a detailed, multidimensional investigation of atmospheric circulation, chemical phase transitions, and supersonic wind patterns across an alien world. Ultimately, HD 189733b serves as an enduring reminder of how deceptive cosmic appearances can be. From afar, its deep blue hue presents a poetic visual parallel to our own world. Yet beneath that azure veil lies a fiercely alien environment shaped by astronomical proximity and unrelenting thermodynamics. By testing the boundaries of atmospheric science against this turbulent laboratory, researchers continue to refine the analytical tools and observational techniques that will one day help us understand weather patterns across hundreds of other worlds throughout the galaxy. Shifting our perspective from blisteringly hot gas giants to the opposite extreme of the thermal spectrum brings us to the outer reaches of alien planetary architecture, exemplified by the distant world designated as Ogle 2005 BLG 390LB. Located approximately 21,500 light-years away toward the galactic center in the constellation Scorpius, this planet resides in a regime of profound chill and isolation. Unlike the hot Jupiters that circle their hosts in a matter of hours or days, Ogle 2005 BLG 390L traces a wide orbit around a low-mass red dwarf star. The combination of an intrinsically faint parent star and a substantial orbital distance yields an environment where thermal energy is exceedingly scarce, placing this world among the coldest exoplanets ever detected through observational astronomy. To comprehend how astrophysicists located a low-mass planet across thousands of light-years of interstellar space, one must examine the technique responsible for its discovery: gravitational microlensing. Most known exoplanets have been found using the transit method, which measures the slight periodic dimming of a star as a planet crosses its face, or the radial velocity method, which detects the subtle wobble of a star caused by the gravitational tug of an orbiting body. Both of these approaches exhibit a strong observational bias toward massive planets situated close to their host stars. Gravitational microlensing operates on an entirely distinct physical principle rooted in Albert Einstein's general theory of relativity. General relativity establishes that mass warps the fabric of space-time, causing the trajectory of light rays to bend when passing near a massive object. In a gravitational microlensing event, a foreground star aligns almost perfectly with a more distant background source star, as seen from our vantage point on Earth. The gravitational field of the foreground star acts as a natural cosmic lens, bending and focusing the light from the background star, which causes the background star to temporarily brighten in a smooth, predictable, symmetric curve over several weeks or months. If the foreground lens star possesses an orbiting planetary companion, and if the alignment is exceptionally precise, the gravitational field of the planet introduces a secondary, short-lived perturbation into the light curve, manifesting as a sharp, transient spike in brightness. In the case of Ogle 2005 BLG 390LB, this planetary anomaly lasted for less than a day, captured through the collaborative monitoring efforts of several international observing networks, including the Optical Gravitational Lensing Experiment and the Probing Lensing Anomalies Network. Because microlensing relies on the mass of the lensing body, rather than the light it emits, it provides a unique capability to detect low-mass planets at vast distances from Earth and at wide orbital separations from their parent stars. However, this powerful method also introduces significant scientific limitations. Microlensing events are non-repeating, one-time geometric alignments. Once the foreground lens moves out of direct line-of-sight alignment with the distant source star, the magnifying effect vanishes permanently. Consequently, astronomers cannot revisit the system to conduct repeat observations, continuous monitoring, or direct atmospheric transit spectroscopy. Despite these observational constraints, the mathematical modelling of the light curve allowed researchers to place robust constraints on the mass and orbital parameters of the system. The data indicates that the host star is a cool red dwarf with a mass estimated to be roughly 1/5 to 1/3 the mass of our Sun. The planet itself possesses an estimated mass of approximately 5.5 times that of Earth, categorizing it as a super-Earth or a sub-Neptune body. Its orbital distance from the host star is estimated to be roughly 2.6 astronomical units, which is between 2 and 3 times the distance separating Earth from the Sun. In our solar system, an orbital separation of 2.6 astronomical units corresponds to the inner region of the asteroid belt, where solar radiation remains sufficient to maintain temperatures above absolute zero by a considerable margin. Around a low-mass red dwarf, however, the energetics are drastically different. Red dwarf stars exhibit very low bolometric luminosities, often radiating less than 1% of the energy output of our Sun, receiving only a tiny fraction of the stellar flux that Earth receives. Ogle 2005 BLGE 390LB sits far beyond what astronomers define as the stellar snow line, the critical orbital boundary beyond which volatile compounds such as water, ammonia, and methane naturally freeze into solid ice. Because direct thermal emissions from Ogle 2005 BLG 390LB cannot be observed with contemporary instrumentation, scientists must rely on theoretical energy balance models to estimate the thermal state of the planet. Under the simplest theoretical assumptions, assuming the planet absorbs a standard fraction of incident starlight and re-radiates that energy uniformly into space without the influence of an atmosphere, researchers calculate an equilibrium temperature of approximately 50 Kelvin, which translates to roughly -220 degrees Celsius. At this frigid temperature, liquid water cannot exist on the surface, and even gases like nitrogen or methane might condense into solid frost or icy deposits. Planetary scientists approach these temperature values with deliberate hedging and scientific caution. The calculated figure represents a theoretical equilibrium estimate rather than a directly measured surface temperature. Several unknown physical variables could alter the true thermal state of the planet. The foremost uncertainty lies in the presence, thickness, and chemical composition of any potential atmosphere. If the planet retained a substantial gaseous envelope rich in greenhouse gases, such as molecular hydrogen or carbon dioxide, the surface could experience a degree of thermal insulation, raising the base temperature somewhat above the simple black-body equilibrium calculation. Conversely, a highly reflective surface layer of pristine ice would increase the planetary albedo, reflecting most of the meager incoming stellar radiation back into space and cooling the planet even further. Another critical factor that models must consider is internal geothermal heating. In rocky and icy worlds of several Earth masses, the radioactive decay of long-lived unstable isotopes such as uranium, thorium, and potassium, combined with residual heat from gravitational accretion during planetary formation, can generate a persistent internal heat flux. On a world where the surface is locked in a deep freeze, this subterranean thermal energy could theoretically maintain a subsurface liquid layer beneath a thick exterior crust of water ice, analogous to the hypothesized conditions beneath the icy shells of moons like Europa or Ganymede in our own solar system. However, without direct spectral data or physical samples, the existence of such subsurface oceans remains purely speculative and represents a theoretical deduction rather than an established empirical fact. The internal structure and composition of OGLE 2005 BLG 390L also remain open areas of astrophysical discussion. Given its estimated mass of 5.5 Earth masses, planetary formation models suggest two primary structural scenarios. The first scenario posits a predominantly rocky and icy body with a dense metallic core, a silicate mantle, and a massive outer shell of water ice mixed with other volatile compounds. The second scenario proposes a miniature gas-rich world possessing a rocky core, enveloped in a tenuous layer of hydrogen and helium gas captured from the protoplanetary nebula before dissipation. Because microlensing yields mass ratios rather than physical radii, determining which of these structural models accurately reflects reality remains beyond the reach of current observational data. The significance of OGLE 2005 BLG 390LB extends far beyond its record-setting low-temperature estimates. Its discovery provided the first concrete observational evidence that small, cold, terrestrial mass planets can successfully form and endure around low-mass stars at wide orbital separations. Prior to this detection, observational surveys were predominantly populated by massive, scorching gas giants, leading some early models to question whether smaller, icy worlds could assemble efficiently in the outer regions of low-mass stellar disks. The microlensing light curve of this distant system proved that planetary accretion processes operate effectively across diverse stellar environments, populating the galaxy with cold, low-mass bodies that standard radial velocity and transit surveys routinely overlook. Ultimately, OGLE 2005 BLG 390LB illustrates both the power and the boundaries of modern astrophysics. It shows how the bending of light across tens of thousands of light-years can reveal the presence of a frigid super-Earth quietly orbiting in the galactic depths. At the same time, it highlights the essential role of scientific prudence when interpreting derived physical properties. While the precise details of its atmospheric composition, surface geology, and exact thermal profile remain unmeasured, the existing data firmly establish this world as a testament to the staggering thermal diversity that characterizes the planetary systems of our Milky Way galaxy. Deep within the constellation Auriga, approximately 1,400 light-years from Earth, resides a planetary system undergoing one of the most violent gravitational dramas ever observed in astrophysics. At the center of this cosmic arena is WASP-12b, an ultra-hot gas giant discovered in the late 2000s by the Wide-Angle Search for Planets Consortium. While many hot Jupiters push the boundaries of planetary physics through sheer thermal intensity, WASP-12b exists in a category of extreme peril. It is a world caught in a terminal gravitational embrace with its parent star, providing scientists with an unprecedented, real-time laboratory to study the physical mechanisms that govern tidal disruption orbital decay, and the ultimate destruction of a planet. To comprehend the existential crisis confronting WASP-12b, one must examine its orbital geometry. The host star, WASP-12, is a yellow-white dwarf star slightly more massive, hotter, and more luminous than our Sun. WASP-12b orbits this stellar host at a distance of approximately 3,400,000 kilometers, completing an entire revolution in roughly 26 hours, or just over 1 Earth day. To put that separation into perspective, the planet orbits at a distance roughly 1/10 the separation between Mercury and the Sun, skimming the outer atmosphere of its parent star at orbital velocities exceeding 200 kilometers per second. At such close quarters, classical planetary assumptions break down entirely. Under normal conditions throughout the solar system, massive gaseous planets maintain a roughly spherical geometry, governed primarily by their self-gravity and hydrostatic equilibrium, modified slightly by rotational flattening at their poles. For WASP-12b, however, the gravitational field of the host star exerts immense differential forces across the body of the planet. Because gravitational acceleration diminishes rapidly with distance, the hemisphere of WASP-12b facing the star experiences a significantly stronger gravitational pull than the hemisphere turned away. This differential acceleration produces overwhelming tidal forces that stretch the gas giant along the axis connecting the centers of mass of the planet and the star. Rather than remaining spherical, WASP-12b is deformed into an elongated prolate spheroid, taking on an egg-like or rugby ball shape. Hydrodynamic simulations and optical light curve modeling suggest that the planet is stretched so severely that its equatorial diameter aligned with the star is significantly larger than its polar diameter. This tidal distortion represents a planet pushed to the absolute edge of its Roche lobe, the theoretical three-dimensional boundary within which planetary material is gravitationally bound to the planet itself, rather than being captured by the host star. The consequences of filling its Roche lobe are profound. As the outer atmospheric layers of WASP-12b heat up and expand under relentless stellar irradiation, the outermost gas crosses the inner Lagrangian point, designated as the L1 point, where the gravitational attraction of the planet and the star balance out. At this gravitational threshold, the planet can no longer retain its upper atmosphere. Gaseous material, primarily composed of hydrogen, helium, and vaporized heavy elements, spills continuously across the Lagrangian point toward the host star. This atmospheric mass transfer is thought to form an extensive accretion stream and a circumstellar shroud of ionized gas encircling the entire system. Ultraviolet transit spectroscopy conducted with the Hubble Space Telescope revealed compelling evidence supporting this mass loss mechanism. When observing the planet in near ultraviolet wavelengths, astronomers detected an early ingress, meaning that the star began to dim in ultraviolet light significantly before the optical silhouette of the planetary disk crossed the stellar face. Astrophysical models interpret this phenomenon as an asymmetric, diffuse cloud of escaped planetary gas moving ahead of the planet in its orbital path, absorbing stellar light before the core of the planet arrives. High-resolution spectroscopic observations have also detected absorption signatures of vaporized metals, including neutral and ionized magnesium, calcium, and iron, within this expanding exosphere. Theoretical estimates suggest that WASP-12b may be shedding atmospheric mass at a rate of several billion to tens of billions of kilograms every single second. While this mass loss rate sounds staggering in absolute terrestrial terms, the gas giant is roughly 1.4 times more massive than Jupiter, meaning that mass loss alone might not necessarily strip the planet entirely during the remaining lifetime of the host star. Instead, a far more catastrophic physical mechanism is driving WASP-12b toward its demise: orbital decay. For over a decade, international teams of astronomers tracked the precise timing of WASP-12b as it transited its host star, cataloguing hundreds of transit events across multiple ground-based and space-based observing facilities. As the observational baseline extended, researchers uncovered a subtle but systematic anomaly in the data. The orbital period of WASP-12b was steadily decreasing. The transits were consistently occurring earlier than predicted by models assuming a constant orbital period, with the orbit shrinking by approximately 29 milliseconds every year. This measurement provided the first unambiguous evidence of an exoplanet actively spiraling inward toward its parent star. In the early years following this discovery, scientists debated two competing theoretical interpretations. The first hypothesis posited that the observed timing variations were caused by apsidal precession, a phenomenon where the orbital ellipse slowly rotates in space due to gravitational perturbations or relativistic effects, mimicking orbital decay without an actual loss of orbital energy. The second hypothesis proposed genuine tidal dissipation, where gravitational interactions between the planet and the star transfer orbital energy into internal heat within the star, causing the orbit to contract continuously. Subsequent long-term observational campaigns, supported by continuous photometric monitoring from space missions like the transiting Exoplanet Survey satellite, provided critical data that strongly favored the tidal dissipation model over apsidal precession. Because the orbital eccentricity of WASP-12b is extremely small, the precession hypothesis failed to match the consistent, parabolic decrease in transit arrival times observed over a span of more than 12 years. The physics underlying this orbital decay involves a complex exchange of angular momentum and energy. Because WASP-12b orbits its host star faster than the star itself rotates on its axis, the tidal bulge raised by the planet on the stellar surface lags behind the orbital position of the planet. This gravitational misalignment creates a continuous backward torque on the planet, pulling it backward in its orbit. This tidal drag robs the planet of its orbital angular momentum, which is dissipated as turbulent heat within the convective envelope of the star. As the planet loses orbital energy, its orbital radius inexorably shrinks, putting it closer to the star and accelerating the rate of orbital decay in a vicious gravitational feedback loop. The central debate among astrophysicists now focuses on the precise dissipation efficiency within the host star, quantified by the stellar tidal quality factor. Because this factor depends intimately on the complex interior structure, fluid dynamics, and evolutionary state of the star, theoretical estimates can vary. Based on the measured rate of orbital period decrease, current mathematical models project that WASP-12b has a remaining lifetime estimated between 2.5 million and 10 million years. In astronomical terms, where planetary systems typically endure for billions of years, a lifespan of a few million years is a fleeting moment, indicating that humanity happens to be observing this planetary system during the final phase of its existence. Beyond its mechanical destruction, WASP-12b presents extreme thermal and atmospheric properties. The dayside temperature of the planet is estimated to exceed 2,200 degrees Celsius, rendering its upper atmosphere hot enough to vaporize rock and metals. Spectrophotometric measurements have revealed that the planet exhibits an exceptionally low geometric albedo, reflecting less than 10% of incident optical light. This makes WASP-12b appear almost pitch black across visible wavelengths, absorbing nearly all incoming stellar radiation and re-emitting that energy primarily as intense thermal infrared radiation. Furthermore, chemical equilibrium analyses have sparked lively discussions regarding the atmospheric composition of WASP-12b, particularly concerning its carbon-to-oxygen ratio. Early spectroscopic studies suggested that the planet might possess a carbon-rich atmosphere, where carbon monoxide and methane dominate over water vapor, leading some theoretical models to propose exotic interior mineralogies rich in carbides and diamond-like structures. However, subsequent high-resolution spectroscopic studies have urged caution, emphasizing that atmospheric three-dimensional dynamics, spatial thermal gradients, and photochemical processes can mimic carbon-rich spectral signatures without requiring an anomalous elemental abundance. In conclusion, WASP-12b serves as an extraordinary case study in planetary astrophysics, bridging the domains of orbital mechanics, stellar interior physics, and atmospheric escape. It demonstrates that the survival of a planet is not guaranteed once formed, but remains subject to the relentless gravitational forces exerted by its stellar host. While theoretical simulations continue to refine the exact timeline of its destruction, the empirical data gathered from WASP-12b offer a direct, quantifiable glimpse into the inevitable death of an ultra-hot world, slowly being torn apart and consumed by the star it orbited for millions of years. Leaving behind the fierce tidal destruction of closely orbiting hot Jupiters, we turn our attention to an entirely different class of astronomical complexity, where the very architecture of a planetary system defies the classical models established by our own solar system. Located approximately 245 light-years away in the constellation Cygnus, Kepler-16b represents a monumental milestone in planetary astrophysics. It is the first unambiguously confirmed circumbinary planet, a world that orbits not one, but two stars simultaneously. For decades, the existence of such planets was relegated to the realm of theoretical physics and science fiction. The confirmation of Kepler-16b demonstrated definitively that nature can forge and maintain planetary bodies in the complex, shifting gravitational environments of binary star systems, prompting a fundamental re-evaluation of planetary orbital mechanics and formation theories. To appreciate the intricate orbital ballet of Kepler-16b, it is essential to first understand the stellar duo at the center of the system. The primary star, Kepler-16a, is an orange K-type main sequence star, possessing approximately 69% of the mass of our Sun. Its companion, Kepler-16b, is a much smaller and cooler red M-type dwarf, with a mass roughly 20% that of the Sun. These two stars are locked in a mutual gravitational embrace, orbiting a common center of mass, known as a barycenter, every 41 days. The distance between the two stars is remarkably small, roughly equivalent to a fifth of the distance between Earth and the Sun. Orbiting outside this central stellar pair is the planet Kepler-16b, a gas giant with a mass roughly equivalent to that of Saturn. It completes a full revolution around the central binary system roughly every 229 days, at a distance roughly similar to the orbit of Venus in our solar system. In astrophysical terminology, Kepler-16b occupies a p-type orbit, meaning it circles the entire binary system, as opposed to an S-type orbit, where a planet would circle only one of the individual stars within a widely separated binary. The gravitational dynamics governing a p-type circumbinary orbit are immensely complicated. In a single star system like our own, the gravitational relationship between the star and a planet can be approximated by classical two-body Keplerian mechanics, resulting in stable, predictable elliptical orbits. However, introducing a second massive star transforms the system into an iteration of the infamous three-body problem. Because the two central stars are continuously moving around their barycenter, the gravitational vector acting on the orbiting planet is never constant. The strength and direction of the gravitational pull fluctuate continuously, depending on where the two stars are in their 41-day mutual orbit relative to the position of the planet. This constantly shifting gravitational terrain means that the orbit of Kepler-16b is not a perfect closed ellipse. Instead, its orbital parameters, including its eccentricity and the orientation of its orbital plane, undergo continuous cyclical variations. Astronomers rely on heavy computational numerical integration to model these orbital perturbations. These theoretical models define a critical boundary known as the dynamical stability limit. If a circumbinary planet forms or migrates too close to the central stars, the gravitational resonances and shifting forces will inject chaotic energy into the orbit of the planet. Over astronomical timescales, this chaotic interaction typically results in the planet either being violently ejected from the system into interstellar space or crashing into one of the host stars. Remarkably, Kepler-16b exists on the absolute precipice of this stability boundary. Calculations suggest that if its orbit were even marginally closer to the central binary, the gravitational perturbations would render its path unstable. This precarious positioning raises profound questions regarding the formation history of the planet. Current theoretical models of planetary accretion suggest that it is incredibly difficult, if not impossible, for a planet to form in situ, exactly where Kepler-16b currently resides. Within a circumbinary protoplanetary disk, the gravitational torque generated by the central binary system violently stirs the surrounding disk of gas and dust. This continuous disruption excites the orbital eccentricities of the microscopic dust grains and larger planetesimals. Instead of gently colliding and sticking together to build planetary cores through constructive accretion, these rocky fragments would likely crash into one another at highly elevated, destructive velocities, shattering into smaller debris rather than coalescing. Because of this harsh dynamic environment, astrophysicists hypothesize that Kepler-16b must have formed much further out in the stellar system, within a calmer, more stable region of the primordial disk. Over millions of years, gravitational interactions with the surrounding gas and dust disk likely drained the planet of its orbital momentum, causing it to slowly migrate inward until the dissipation of the gas disk halted its journey just outside the critical stability radius. The unique geometry of the Kepler-16 system also presented an extraordinary challenge for observational astronomy. Most transiting exoplanets are detected by observing the periodic, rhythmic dimming of a single host star. A planet in a simple circular orbit around a single star will produce transit signals with a highly precise clock-like regularity. For a circumbinary planet, this predictable metronome is shattered. Because the two host stars are constantly changing their positions relative to each other and to the observer, the planet does not cross the face of the stars at regular intervals. A transit might occur earlier or later than expected by a margin of several days, depending on whether the primary star happens to be moving toward or away from the planet at the moment of alignment. To definitively confirm the existence of Kepler-16b, astronomers had to disentangle an incredibly complex web of overlapping light curves. They had to account for the primary star eclipsing the secondary star eclipsing the primary star, the planet transiting the primary star, and the planet transiting the secondary star. The successful modelling of these transit timing variations stands as a triumph of modern computational astrophysics, proving that our instruments and analytical frameworks have grown sophisticated enough to map the most chaotic and variable gravitational environments in the galaxy. The discovery of circumbinary planets like Kepler-16b has also forced scientists to fundamentally redefine the concept of the habitable zone. In a traditional planetary system, the habitable zone is visualized as a static, spherical shell surrounding a star, wherein a terrestrial planet receives just the right amount of stellar insolation to maintain liquid water on its surface. In a binary star system, the boundaries of the habitable zone are entirely dynamic. Because the two stars possess different luminosities and are continuously changing their proximity to the planet, the amount of radiative energy reaching a circumbinary world fluctuates in complex cyclical patterns. Theoretical climatologists who simulate planetary atmospheres in these environments must account for this pulsating radiation field. A planet orbiting a binary system would experience significant variations in thermal energy on relatively short timescales, potentially driving extreme atmospheric circulation and rapid climatic shifts. However, sophisticated atmospheric models suggest that if a planet possesses a sufficiently thick atmosphere and extensive global oceans, the thermal inertia of those systems could buffer the planet against the worst of the stellar fluctuations, effectively smoothing out the chaotic energy input and maintaining a relatively stable surface climate. It is important to emphasize with scientific caution that Kepler-16b itself is not considered a candidate for habitability. As a Saturn mass gas giant, it lacks a solid surface, and its orbital distance places it outside the outer edge of the theoretical circumbinary habitable zone for this specific stellar pair. Based on equilibrium temperature calculations, the planet is estimated to be incredibly cold, with temperatures resembling the freezing conditions of dry ice, hovering around -100 to -70 degrees Celsius. Any atmospheric water vapor would be thoroughly frozen into deep cloud decks. Never, the confirmed existence of stable circumbinary planets fuels the fascinating, albeit currently speculative, hypothesis regarding exomoons. If a gas giant located within a dynamic circumbinary habitable zone were to harbour a large rocky moon, that satellite could theoretically possess the conditions necessary for complex chemistry. A moon in such a system would experience an exceptionally complex sky, with two suns continuously altering their separation, occasionally eclipsing one another and casting dual shadows across the landscape. Ultimately, the analysis of Kepler-16b and its orbital mechanics illustrates that our galaxy is far more architecturally diverse than classical astronomy once presumed. It provides a vital theoretical framework for understanding the limits of gravitational stability, demonstrating that the chaotic interactions of the three-body problem can occasionally settle into a precarious, long-term harmony. As astronomical surveys continue to probe multi-star systems, researchers anticipate discovering many more of these circumbinary worlds, each one serving as a rigorous test for our computational models of planetary formation and celestial mechanics. In our exploration of extreme worlds, we have examined planets subjected to blistering stellar radiation, supersonic mineral winds, freezing orbital separations, and violent gravitational destruction. Yet all of these systems share a common cosmic anchor. They revolve around at least one host star. As astronomers expanded their observational capabilities and theoretical frameworks, they uncovered an even more radical population of worlds that lack any stellar parentage entirely. These are the free-floating planets, often referred to as interstellar nomads or rogue planets. Drifting through the vast, cold chasms separating the stars of our galaxy, these sunless bodies do not participate in a traditional planetary system. Instead, they orbit only the distant collective gravitational center of the Milky Way, challenging our fundamental definitions of what constitutes a planet and how planetary architectures evolve. Detecting an object that possesses the mass of a planet but emits virtually no light of its own presents one of the most formidable hurdles in observational astronomy. Because rogue planets do not transit a parent star, nor do they induce measurable radial velocity wobbles in a stellar host, traditional exoplanet hunting techniques are largely ineffective. To capture empirical evidence of these solitary travelers, astrophysicists rely primarily on two specialized observation strategies: gravitational microlensing and wide-field infrared imaging of young star-forming regions. As established in the study of distant icy worlds, gravitational microlensing occurs when the gravitational field of a foreground mass acts as a natural cosmic lens, temporarily magnifying the light of a more distant background star. When a free-floating planet crosses the line of sight between Earth and a background source, it produces an exceptionally brief, isolated brightening event. Because the duration of a microlensing event is directly proportional to the square root of the lens mass, a typical stellar lens magnifies background light over several weeks or months, whereas a rogue planet creates an anomaly that lasts for only a few hours to a couple of days. Surveys such as the optical gravitational lensing experiment and the microlensing observations in astrophysics collaboration have documented a growing catalogue of these short-duration lensing signals. In several remarkable detections, the light curves exhibited no secondary signatures of an accompanying host star within several astronomical units of the lensing body, strongly supporting the interpretation that these objects are isolated, low-mass nomads traveling through the interstellar medium. Complementary to microlensing, astronomers have utilized high-sensitivity infrared telescopes to directly image young, self-luminous rogue candidates within stellar nurseries, such as the Upper Scorpius and Orion star-forming complexes. During the first few tens of millions of years following their assembly, massive gaseous bodies still retain significant thermal energy generated during gravitational accretion. At this early evolutionary stage, they radiate weakly across near-infrared and mid-infrared wavelengths, allowing instruments to characterize their temperatures, surface gravities, and atmospheric absorption bands before they cool into near-total optical obscurity. The confirmed existence of these unattached worlds raises a paramount astrophysical question. How does a planet-mass body end up drifting alone through interstellar space? Contemporary astrophysics proposes two primary formation pathways, each governed by distinct physical and mathematical mechanisms: dynamic gravitational ejection from an existing planetary system and direct in situ collapse from a molecular gas cloud. The most widely supported model for the majority of lower-mass rogue planets is dynamical ejection, driven by planet-planet scattering. When planetary systems assemble from circumstellar protoplanetary disks, they frequently undergo periods of severe dynamical instability. Computational n-body numerical simulations, which calculate the mutual gravitational forces exerted among multiple interacting bodies over millions of orbital cycles, demonstrate that newly formed multi-planet systems are rarely born in perfectly stable, permanent configurations. In the early stages of system evolution, massive gas giants and terrestrial protoplanets often share congested, overlapping orbital corridors. While the surrounding primordial gas disk remains present, hydrodynamic friction and gas drag act as natural stabilizing mechanisms, circularizing planetary orbits and dampening chaotic eccentricities. However, as the parent star ignites and stellar winds clear away the remnant gas, this hydrodynamic damping vanishes. The system transitions into a regime dominated purely by nonlinear gravitational interactions. Over millions of years, repeating orbital resonances, where planets periodically align at the same relative positions, can systematically pump kinetic energy and eccentricity into the orbits of the interacting bodies. Eventually, two or more massive planets experience an exceptionally close gravitational encounter. During such an event, the conservation of angular momentum and energy dictates that one planet will be gravitationally scattered inward, while the other is accelerated outward. In a significant fraction of these close encounter simulations, the lighter planet absorbs enough orbital energy from the more massive body to exceed the local escape velocity of the host star. Mathematically, if the kinetic energy imparted to the scattered planet surpasses the gravitational potential energy binding it to the stellar host, the trajectory of the planet transforms from a closed, elliptical bound orbit into an open, unbound hyperbolic trajectory. The planet accelerates past the outer boundaries of its native system, severing its gravitational tether to the parent star and embarking on an indefinite journey across interstellar space. Meanwhile, the surviving planet is typically knocked into an eccentric, highly tilted orbit, a theoretical outcome that aligns remarkably well with the large number of highly eccentric exoplanets observed in catalogued multi-planet systems. A secondary dynamical mechanism for ejection involves external environmental perturbations within dense stellar birth clusters. Most stars, including our Sun, do not form in complete isolation. They are born in crowded stellar nurseries populated by hundreds or thousands of sibling stars. In these compact environments, the average distance between neighboring stellar systems is dramatically smaller than it is in the current galactic neighborhood. Numerical models of cluster dynamics reveal that close stellar flybys, where a passing star traverses the outer perimeter of a neighboring planetary system, can violently disrupt the gravitational equilibrium of outer planets. These external gravitational shearing forces can strip loosely bound worlds from their orbits, casting them into the galactic void or leaving their systems dynamically crippled, precipitating internal scattering events that ultimately lead to further ejections. In contrast to the ejection hypothesis, an alternative theoretical pathway posits that some rogue objects, particularly those at the higher mass end of the spectrum, may have formed independently through direct gravitational collapse. In classical star formation theory, a dense interstellar gas cloud collapses under its own self-gravity when its mass exceeds a threshold known as the Jeans mass. As the cloud contracts and fragments into smaller clumps, it typically forms stars or low-mass brown dwarfs. However, theoretical astrophysicists continue to debate the absolute minimum mass limit for cloud fragmentation, known as the opacity-limited Jeans mass. Standard theoretical models suggest that when a collapsing gas pocket becomes optically thick to its own radiation, it can no longer cool efficiently, halting further fragmentation. This physical boundary is widely estimated to occur between 1 and 5 times the mass of Jupiter. Objects forming via this direct collapse mechanism are often designated by astrophysicists as sub-brown dwarfs. Distinguishing whether an isolated multi-Jupiter mass object originated from cloud fragmentation like a star, or from gravitational ejection like a true planet, remains an open observational challenge, as both processes can yield objects of comparable masses and surface temperatures in the interstellar field. The physical and atmospheric conditions of a sunless planet represent an extraordinary frontier of theoretical climatology. In the absence of an external stellar furnace, the surface of a rogue planet is exposed exclusively to the ambient cosmic microwave background radiation and faint starlight, dropping the incoming equilibrium temperature to near absolute zero. Yet, theoretical models propose that a rogue planet is not necessarily a completely dead or inert world. In the late 1990s, planetary scientist David Stevenson formulated a groundbreaking theoretical hypothesis regarding the thermal evolution of terrestrial mass rogue planets. If an Earth-sized rocky planet is violently ejected from its native system, it might retain a thick, dense atmosphere composed predominantly of primordial molecular hydrogen captured during its formation. Molecular hydrogen is an exceptionally volatile gas that does not readily condense into liquid or ice, even under extreme cold. Under the immense atmospheric pressures characteristic of a heavy gas envelope, hydrogen molecules undergo a quantum mechanical process called collision-induced absorption, wherein molecular collisions create temporary dipole moments that absorb infrared radiation with extraordinary efficiency. According to these theoretical calculations, a thick hydrogen atmosphere could provide profound thermal insulation, effectively trapping the persistent internal geothermal heat generated by the radioactive decay of long-lived unstable isotopes such as uranium, thorium, and potassium, as well as residual heat from core formation. Stevenson's mathematical models suggested that this geothermal heat flux, while minuscule compared to solar insolation on Earth, could potentially maintain surface temperatures above the freezing point of water, theoretically allowing liquid water oceans to persist directly beneath a dense, sunless sky. Scientists treat this scenario with rigorous hedging and careful skepticism. While mathematically sound within the boundaries of idealized thermodynamic equations, such models rely on unverified assumptions regarding the efficiency of atmospheric retention during the violent mechanical processes of planetary ejection. Furthermore, without a parent star to drive photochemistry, the atmospheric chemistry and long-term stability of such worlds remain purely theoretical constructs that cannot yet be empirically validated. Looking toward the broader galaxy, statistical extrapolations derived from microlensing surveys suggest that rogue planets are not rare anomalies, but rather a substantial galactic population. Some demographic models project that there could be as many, or even more, free-floating planets drifting through the Milky Way as there are main-sequence stars, potentially numbering in the hundreds of billions. Upcoming space observatories, specifically the Nancy Grace Roman Space Telescope, are designed to conduct expansive, high-precision gravitational microlensing surveys of the galactic bulge. These upcoming missions are projected to discover hundreds of rogue planets spanning a wide range of masses, from massive gas giants down to Earth mass and Mars mass terrestrial nomads. The data gathered from these missions will provide the first robust statistical census of the rogue population, establishing empirical constraints on planetary mass functions and allowing astrophysicists to test the competing mathematical models of planetary scattering versus direct gravitational collapse. Ultimately, rogue planets stand as profound testaments to the dynamic, often chaotic nature of planetary systems. They illustrate that the formation of a planetary system is not a gentle static process, but a competitive gravitational arena where some worlds find stable orbits around their suns, while countless others are cast out into the interstellar darkness. Drifting in perpetual twilight through the vast gulfs between the stars, these sunless worlds remind us that planetary physics operates on a scale far grander and far more turbulent than what we observe in the quiet order of our own solar neighborhood. As we contemplate these radical alien environments, an essential question inevitably arises. How can astrophysicists determine the atmospheric chemistry, temperatures, and dynamic weather patterns of worlds orbiting stars tens, hundreds, or even thousands of light-years away? The answer lies within one of the most powerful analytical techniques in modern astrophysics: spectroscopy. Because our current telescopes cannot directly resolve the surfaces of distant exoplanets, scientists treat light itself as an information-rich cosmic messenger. When an exoplanet passes directly in front of its parent star during a transit event, a minute fraction of the stellar light filters through the outer ring of the planetary atmosphere before continuing its journey toward our space-based and ground-based observatories. This technique, known as transmission spectroscopy, relies on fundamental quantum mechanics. Every atomic and molecular species possesses a unique set of quantized energy states. When starlight passes through the atmospheric gas, atoms and molecules selectively absorb very specific wavelengths of electromagnetic radiation, corresponding precisely to the energy needed to excite electrons or vibrate molecular bonds. For instance, vaporized water, methane, carbon dioxide, carbon monoxide, and atomic elements like sodium and iron each absorb light at distinct characteristic wavelengths. By dispersing the incoming starlight into a detailed spectrum and measuring the minute fluctuations in brightness across different wavelengths, astronomers can detect these telltale absorption signatures. The missing wavelengths function as a chemical fingerprint, allowing researchers to infer the presence, abundance, and vertical distribution of specific atmospheric gases. Similarly, emission spectroscopy measures the thermal radiation emitted directly by the planet itself, typically observed just before or after the planet passes behind its host star in an event known as a secondary eclipse. By analyzing how much infrared light disappears when the planet is occulted by the star, scientists can construct broad thermal maps and estimate daytime temperatures across alien skies. However, interpreting these spectral signatures demands tremendous scientific rigor and deliberate caution. The spectral variations caused by an exoplanet atmosphere are extraordinarily subtle, often amounting to less than 0.1% of the total starlight. Planetary scientists must utilize complex mathematical algorithms and three-dimensional atmospheric retrieval models to disentangle these tiny signals from instrumental noise, stellar activity like star spots and flares, and overlapping chemical absorption bands. Therefore, our current portraits of these extreme exoplanets are not static, definitive depictions, but rather sophisticated, data-driven working hypotheses. As next-generation observatories like the James Webb Space Telescope continue to collect higher-resolution spectroscopic data, and as upcoming ground-based facilities like the Extremely Large Telescope come online, our theoretical models will inevitably be refined, updated, or in some cases fundamentally rewritten. The iterative process of science does not declare absolute finality. It continually gathers new evidence to bring our understanding of the universe into sharper focus. From the vaporized iron skies of Kelt 9b and the supersonic silicate torrents of HD 189733b to the frigid silence of Ogle 2005 BLG 390LB, the tidal distortion of WASP 12b, the orbital complexities of circumbinary systems like Kepler 16b, and the sunless expanse traversed by rogue planets, each discovery reveals that the laws of physics can assemble worlds far more diverse and extreme than humanity ever envisioned. These planets remind us that our solar system is just one chapter in an immense, dynamic cosmic library. As we continue to look outward, decoding the faint whispers of light traveling across the void, we are only beginning to comprehend the true extent of planetary diversity across the galaxy. Thank you for joining us on this exploration of the extreme cosmos, and until next time, keep looking up.